In our last lesson, we started talking about nuclear reactions, fission and fusion. And we said that when those reactions occur, we get a lot of energy produced. And where does the energy come from? It turns out that some mass is destroyed in these reactions. Okay? Now, one of the fundamental laws of chemistry is that matter cannot be created or destroyed, and it turns out that it's not true. When they started studying nuclear reactions, they found that some mass was destroyed. So mass can be converted into energy. Now, Einstein is famous for the equation E equals mc squared. We're going to use that equation to find the energy created when matter is destroyed. E is going to be energy in joules, m is the mass destroyed in kilograms, and c is the speed of light. It's a constant. It's always 3 times 10 to the 8th. So for this example, we're going to see how much energy is created if 1 gram of matter is destroyed. So our mass that's being destroyed is 1 gram. And we want to be in kilograms. Kilo means 1,000, so I got to divide by 1,000 or move 3 places. So that's going to give me 0.001 kilograms. Then if I plug into E equals mc squared, I'm going to get 0.001 times 3 times 10 to the 8th squared. And when I do that, I'm going to get an energy of 9 times 10 to the 13th joules. Now I'm going to write that number out just so we get a feeling for it. It's going to be 9 followed by 13 zeros. Joules. So that is an awful lot of energy just by destroying 1 gram of matter. So if we could figure out how to destroy 1 gram of matter, we would get that much energy created. Now here's another example. Okay, in the fusion reaction above, deuterium and tritium combine to form helium. So I'm going to write out that equation. I have deuterium, which is a fancy form of hydrogen. Hydrogen usually is 1, 1. It doesn't have any neutrons. This has an extra neutron, so it has a mass of 2. I'm going to combine that with tritium, which is also a fancy form of hydrogen. This has another extra neutron. When I combine those, we're going to make helium 2,4 plus a neutron. And even though our mass numbers add up, if we have the masses to several significant figures, we can find that the mass of the products is going to be different than the mass of the reactants. Mass of products is going to be different than the mass of the reactants. So these are the products, and I'm going to add those two. And if I add those two up, I end up with a value for the total mass of the reactants of 8.4748 times 10 to the minus 27th kilograms. And then when I add the mass of the products, I get 8.4429 times 10 to the minus 27th kilograms. So as you can see, the mass of the products is less than the mass of the reactants. Some mass got lost. So if we subtract that, we'll get the missing mass, and we end up with a value of 3.19 times 10 to the minus 29th kilograms of missing mass. Now they gave that a name, the missing mass. The word defect means a problem, and this seemed to be a problem because people didn't think we could lose mass. So another word for the missing mass is the mass defect. So if you're ever asked for the mass defect, they're asking for the missing mass. Then if I want to find out how much energy is created in one of these reactions, we're going to do E equals mc squared. So for the m, I just put in the mass that's destroyed or that's missing. So that's the 3.19 times 10 to the minus 29th kilograms. We're going to multiply that by c squared. C is 3 times 10 to the 8th. And we have to remember to square it. And when we do that, we get a value for the energy in just one of these reactions. And we get a value of 2.871 times 10 to the minus 12th joules. Okay. Now, that is a tiny amount of energy, but in just 1 mole of deuterium, which would weigh approximately 2 grams, so only 2 grams of deuterium, there are 6.22 times 10 to the 23rd atoms. That's what a mole is Avogadro's number worth of atoms. So if I was to take 1 mole, 2 grams of this, and combine it with 1 mole of the tritium, let's figure out how much energy I would have then. Okay, so it would be 2.871 times 10 to the minus 12th joules per atom that reacted times 6.02 times 10 to the 23rd atoms, and I would get a value of 1.73 times 10 to the 12th joules of energy. So again, that's an awful lot of energy when I just destroy 2 grams, or I just combine 2 grams of deuterium with 3 grams of tritium. So 5 total grams of reactants gives me that much energy. Now, there's another unit that you can use for energy, and this is kind of like electron volts. It's kind of a shortcut or an easy way to do it. It turns out that for 1 atomic mass unit that I destroy, that gives me 931 MeVs of energy. And MeVs is mega electron volts. We talked about electron volts before, and then mega just means times 10 to the 6th. So for every atomic mass unit, we'll say that this is an atomic mass unit. For every atomic mass unit destroyed, I get 931 joules of, 931 MeVs of energy. So if I have a carbon nucleus, which has a mass of 12 atomic mass units, I want to know how much energy is created, and then I'm going to express it in MeVs. So all I do is take 12 U's, and I multiply it by 931 MeVs per each U. So I'm just going to multiply those two numbers together, and I end up with 11,172 MeVs of energy. No, I'm done. I don't have to convert it to joules because it's just asking me for the energy in MeVs. So here's another example. In a reaction, a neutron decays into an electron and a proton, and I want to know how much energy is created. So from the table at the beginning of the notes, we have the masses, protons, neutrons, and electrons are these values. So I'm going to rewrite the equation here. So I have N01 decaying into a proton and an electron. And I'm going to find out how much mass I have before and how much mass I have after. So the neutron is 1.008665 for its mass. Decays into a proton, which is 1.007276. plus an electron, which is only 5.4857779 times 10 to the minus fourth U's. Now if I add those together, I get a value of 1.007824 U's. Now I can find my missing mass by subtracting those. So the mass defect is equal to 1.008665, which was the mass that I had before the reaction, minus 1.007824. And I end up with a mass defect of 0.0084 U's. Now I need to convert that into energy. If I'm in U's, all I do is multiply by the 931 number. So here it is, energy is going to equal 0.00084 U's times 931 MeVs per U. And when I do that, I get a value of 0.782 MeVs. So I'm just going to explain this to you. The binding energy. So this is the energy per nucleon holding them together. And basically what you have to notice is that right here at 56, the mass number of 56, you have the strongest binding energy. So that's going to be the most stable, okay, and it's iron. Okay, iron 56 is the most stable. So anything smaller than that, you're going to want to do fusion for to get energy out of it, and anything bigger than that, you're going to do fission to get energy out of it. And 56, you wouldn't get any energy out of it by either fusing it with something or trying to do fission with it. So that's what we're saying right here. Okay, matter and antimatter. Antimatter is the opposite of matter. Okay, for every particle that we know of, there's an equivalent antiparticle. It just has the opposite charge. So you have the same particles, but with opposite charges. Okay, so here's an example. Okay, for a proton, the antiparticle is called an antiproton. A proton has a charge of +1. Okay, for a proton, the charge is +1. An antiproton, and to denote an anti, you put a little line over it. So that means an antiproton, the charge of it is -1. So it's the same in every other way. Okay, it'll have the same mass, okay, but it has the opposite charge. Now, when a particle and the antiparticle meet one another, they annihilate each other. Okay, the mass of both is completely turned into energy, so they're completely destroyed, and all that mass turns into energy. So if a proton and an antiproton touch one another, they destroy each other, they're gone, and you get energy out. How much energy, and we're going to do it both in joules and MeVs, is created when an electron and a positron meet. The only antiparticle that doesn't have a name that's just anti is an electron. An antiproton, a proton has an antiproton. A neutron has an antineutron. An electron would have an anti-electron, but they call that a positron. So we're going to make a note that a positron is an anti-electron. Okay, so when we do this, we're going to destroy the mass of a positron and the mass of the electron. So the mass destroyed, so the mass defect is going to equal the mass of the electron plus the mass of the positron, or the anti-electron. So I'll call an electron E minus, positron E plus. So that's going to be 2 times 9.11 times 10 to the minus 31 kilograms. And that's going to give me a value of 1.822 times 10 to the minus 30th kilograms. Now, if I want to find the energy in joules, I have to use Einstein's equation, E equals mc squared. So I take the mass in kilograms of 1.822 times 10 to the minus 30th and multiply it by c is the speed of light, 3 times 10 to the 8th. I have to remember to square that. And I end up with an energy of 1.64 times 10 to the minus 13th joules of energy. To find the energy in MeVs, I have to use the mass defect in atomic mass units. So for this one, our mass defect is again going to be 2 times the mass of an electron, but I want to use the atomic mass unit number. So 5.49 times 10 to the minus 4th joules. And if I do that, I end up with 1.098 times 10 to the minus 3rd joules. Now, if I want the energy in MeVs, I don't use E equals mc squared. I just take the amount of AMUs, so 1.098 times 10 to the minus 3rd, and multiply it by, we'll put the units used, by 931 MeVs per U. And the energy I would get would be 0.102 MeVs. So those two energies are equivalent. So that's something to remember. If I want to find energy created in joules, I use E equals mc squared, and the m has to be in kilograms. If I want to find energy in MeVs, I take the mass in atomic mass units and multiply it by 931. So it's two ways of finding the same thing in different sets of units. The last little piece I just want to talk about. When matter was created in the Big Bang, there's no reason why there should have been as much antimatter created as matter. Yet when we observe the world around us, it is made up almost entirely of matter. If there was a lot of antimatter around, it would be bad, because every time matter touches antimatter, they're both destroyed in a burst of energy. So if there was antimatter around, there'd be the explosions as the antimatter and matter annihilated each other. So scientists still don't know why the universe seems to be made up almost entirely of matter. So that's an unanswered question.